Most people think of the internet as something abstract, a service, a signal. You open a browser, tap an app, and information appears. It feels instantaneous and weightless, as if it exists everywhere and nowhere at the same time. The language we use reinforces this idea. We talk about the cloud. We say data is out there. We imagine wireless connections moving freely through the air, independent of geography or physical limits. In everyday life, that model works well enough. You don't need to think about infrastructure to send an email or watch a video. The system feels smooth, automatic, and largely invisible. But that mental picture is incomplete. Not because it's wrong in spirit, but because it hides the parts of the system that actually determine how the internet behaves. Speed, reliability, cost, fragility. The moments when the internet slows down, goes dark, or fails entirely aren't random. They're consequences of a very real, very physical system operating under constraints. To understand the internet as it actually exists, you have to move away from the idea of a floating digital space and towards something more grounded, something built, maintained, powered, and occasionally broken by human hands. Most people imagine their internet connection as a straight line. Their device connects to a router. The router connects to a provider. The provider connects to the rest of the internet. It feels centralized, almost like a utility pipe. If there's a problem, the assumption is that it's either local, like a bad modem, or distant, like a company outage somewhere far away. In between, the system is treated as a black box. Data goes in. Data comes out. The details don't matter. Another common belief is that the internet is mostly wireless. Phones, laptops, tablets, smart devices, they all connect without visible cables. This creates the impression that information travels primarily through radio waves or satellites. Physical distance seems less relevant. Whether a server is across town or across the ocean, the experience feels similar. From the user's perspective, everything collapses into a single interface, a screen, a loading bar, a connection icon. There's also a tendency to think of the internet as resilient by default, redundant, self-healing, too big to fail. When something breaks, it's framed as an anomaly, a glitch, a temporary disruption. The idea that a small physical event could ripple outward and affect millions of people doesn't fit the common mental model. Large systems, in everyday thinking, are assumed to be stable simply because they're large. What's missing from this picture is structure. The internet isn't a single system. It's a layered network of physical infrastructure, protocols, organizations, and economic decisions. Each layer has its own limitations. Each depends on the others to function. When you remove the metaphors and look at the system as it actually operates, the internet starts to look less like a cloud and more like a machine. At the lowest level, the internet is physical. Data moves through fiber optic cables made of glass. These cables run under streets, through buildings, across countries, and along the ocean floor. Most international data traffic travels through undersea cables, not satellites. These cables are thinner than most people expect, but they carry enormous amounts of information using pulses of light. They follow fixed routes. They land at specific coastal points. They connect to physical facilities that must be powered, cooled, and secured. From those landing points, data flows into data centers. These are large buildings filled with servers, networking equipment, and cooling systems. They consume vast amounts of electricity. They generate heat. They require constant maintenance. When you load a website, your request is routed to a specific machine in one of these facilities, chosen based on location, availability, and cost. There is no universal cloud. There are thousands of privately owned machines distributed unevenly around the world. Between your device and those machines, data doesn't travel in one continuous stream. It's broken into packets. Each packet carries a small piece of information, along with instructions about where it came from and where it's going. These packets move independently, hopping from router to router. Each router makes a local decision about where to send the packet next, based on routing tables and network conditions. If one path is congested or unavailable, packets may take another route. This is why the internet can reroute around damage, but only within the limits of existing infrastructure. The rules governing how packets are created, addressed, sent, and reassembled are defined by protocols. These are agreed-upon standards that allow devices built by different companies in different countries to communicate. Protocols don't move data themselves. They define behavior. They specify timing, error handling, retries, and priorities. When people talk about the internet working, what they're really describing is millions of devices following the same set of rules closely enough to stay synchronized. None of this happens in isolation. Every part of the system depends on power. Data centers shut down without electricity. Network equipment fails without stable voltage. Backup generators can bridge short outages, but fuel is finite. Power grids and communication networks are tightly coupled, even though they're managed separately. When one is stressed, the other often follows. The system is also shaped by economics. Where cables are laid, where data centers are built, and which routes are prioritized all depend on cost, demand, and political agreements. Traffic doesn't always take the shortest path geographically. It takes the cheapest acceptable path. This is why data between two nearby countries might be routed through a third. Efficiency in network terms is not the same as efficiency in physical distance. Once you see the internet as a physical, layered system, certain behaviors start to make more sense. Latency exists because signals take time to travel through fiber and through processing equipment. Congestion happens because routers and links have finite capacity. Outages cascade because many services rely on the same underlying infrastructure. Redundancy helps, but it's never absolute. These structures create second-order effects that aren't obvious at the user level. Centralization, for example, improves efficiency and reduces cost, but it also concentrates risk. When many services rely on the same data centers or network providers, a single failure can affect unrelated platforms simultaneously. What appears as multiple companies going down at once is often one shared dependency failing upstream. There's also an inequality baked into the system. Regions with dense infrastructure enjoy faster, more reliable connections. Areas with sparse investment experience slower speeds and higher costs. This isn't a technical limitation so much as an economic one. The internet reflects the priorities and trade-offs of the societies that build it. Security issues follow similar patterns. Attacks that exploit common protocols or widely used hardware can spread quickly because uniformity is what allows the system to function at scale. Fixing these issues takes time, coordination, and often physical intervention. Software patches don't replace cables. Updates don't generate electricity. Even the idea of wireless depends on wires. Cellular towers connect back to the network through fiber. Wi-Fi routers are only wireless at the final hop. The air carries signals over short distances, but the backbone remains physical. When storms, construction, or accidents damage that backbone, wireless devices are just as affected as wired ones. Understanding these layers doesn't make the internet feel fragile in a dramatic sense. It makes it understandable. The system works remarkably well given its scale and complexity, but it works because of constant effort. Monitoring, maintenance, redundancy planning, incremental upgrades. The internet isn't resilient by accident. It's resilient within bounds defined by physics, economics, and design choices. Seen this way, internet failures stop looking mysterious. They're not glitches in an abstract realm. They're outcomes produced by real systems interacting under stress. A cut cable, a misconfigured router, a power imbalance. Each small issue matters because the system is interconnected. The shift in perspective is subtle but important. The internet isn't a place you visit. It's a machine you use. One that spans continents, consumes resources, and depends on coordination between countless independent actors. When it works, it disappears into the background of daily life. When it doesn't, it briefly becomes visible, reminding you that something solid is doing the work. You don't need to think about these details every time you go online, but recognizing that they exist changes how the system feels. It's no longer magic, it's infrastructure. And like all infrastructure, it shapes what's possible, what's reliable, and what breaks first when conditions change.